Hi, I'm Lachlan Grose, and today I'm going to talk to you about LoopStructural, a new open source 3D geological modelling library. LoopStructural has been developed as part of the Loop project, a new open source 3D probabilistic geological and geophysical modelling platform. Loop is supported by the Australian Research Council, Australian State and Federal Surveys, and we've got collaborators worldwide from geological surveys and universities. Loop has three main components. We have the Geological Knowledge Manager, we have the Geological and Geophysical Modelling, and the Uncertainty and Risk Mitigation. LoopStructural comes under the Geological and Geophysical Modelling module. So in this module, what we want to do is encode structural geological rules into our 3D modelling algorithms. We want to be able to develop new geologically and geophysically constrained inversion methods, and we want to develop joint geology and geophysical inversions. So today I'm going to show you our implicit 3D modeling module that is the forward geological modeling engine for Loop. So just a bit of a rehash. What is implicit surface modeling? So what we want to do with implicit surface modeling is approximate an unknown function that defines the geometry or the distance to a reference horizon. So let's take this example here. We've got four horizons that are represented by the different colors. So we've got yellow, orange, red, and green. So our top horizon can be our reference horizon, and we can assign a value of 0 to this because the distance to this horizon for these observations is 0. The next horizon down, which is the red horizon, we could assign a value of 60 to these. And then the following horizon could be 220, the green, and then the orange ones at the base could be 330. So this means that the distance from orange to top is 330 meters. So what we want to do is approximate some function that captures the geometry or these observations. And there are two ways that we can do this. We can either use a combination of radial basis functions on the observations, or we could use some sort of discrete interpolation approach where we divide our domain into small piecewise functions. Once we've got our implicit function, we can extract the distance to this reference horizon anywhere in our model. So we end up with some continuous function that we can evaluate throughout the model domain. We can extract ISO values, so surfaces of the implicit function, or we could just look at the function along a section. But a 3D model is more than just one surface. A 3D model is how do our surfaces interact? It's incorporating different geological structures. So we want to look at how faults, folds, unconformities fit into it. So in LoopStructural, we use a time-aware approach for modeling geological features. So what this means is we start with the most recent geological feature, which is modeled, and then we model the next geological feature, taking into account what we've already modeled. So for example, if we were modeling a fault, we first model the fault surface. We then incorporate this fault into the modeling of the faulted surface, which could be stratigraphy. Or if there are multiple faults, we have to determine the overprinting relationship between the faults. To model complicated geometries in LoopStructural, we use a concept called structural frames. So structural frames are a structural geology defined coordinate system. So we start with the major structure feature, and we then define another coordinate that's orthogonal to this, which is our structural direction. And then a third coordinate is our intermediate direction. So for modeling folds, we would define the axial surface as our major structural feature. We then define the structural direction as the fold axis. And then we have the intermediate direction being orthogonal to both the fold axis and the fold axial surface direction. For faults, we define the fault surface, and then we define as the major structure feature, and then we define the fault slip direction as the structural direction, and we use the intermediate direction as the fault extent. Folds are integrated into the implicit modeling by defining the geometry of the fold relative to this fold frame. So we're basically looking at what the fold would look like looking down plunge of the fold. We can characterize the geometry of this and add this into our implicit interpolation algorithm. For faults, we actually approach this by defining the geometry of the fault using the fault frame. We then characterize the displacement magnitude of the fault using the coordinates of the fault. So we define a fault volume. We then unfault the observations of the faulted surface, interpolate these in a restored space, and then we can evaluate this continuous surface anywhere in the model using our restoration function. So we're basically integrating the fault kinematics into the implicit surface description. So for more details on how structural frames, folding and faulting are implemented in Loop, have a look at our documentation and the associated publications. Thank you.